Hey guys, what's up? In this talk, I'm gonna talk about our recent work on Ghidra, the reverse engineering tool. Our goal is to push Ghidra to the next level by fixing things, adding features, and introduce more state-of-the-art technologies. Hope you guys enjoy this talk. First, a little bit about me. My name is Zhanzhao, or you might know me as Anthony, my nickname. I work now at the Starcross Technology, responsible for binary analysis part of the Portal Lab. Portal Lab is our lab in Starcross Technology where we research around topics like API security, cloud security, binary analysis, reversing, and so on. I've been playing CTF for some years till now. Since 2017, some friends and me started Team Rocketpig, and I have been playing as Team Rocketpig for about 4 years. Since 2019, I started my team leadership of Team Rocketpig. Luckily, right after we started Team Rocketpig, we were qualified for DEF CON CTF final, and again, that is about 4 years now. Besides DEF CON CTF, we also played many other CTFs and get awards in many of them, such as Zero CTF, WCTF, and many more. Usually, when I don't play CTF, I do some open source developing, especially enthusiasts in reverse engineering and binary analysis tools. And that's why we have this talk today. In this talk, we will be first talking about vanilla Ghidra, how is it like in my personal view. The next thing I'm gonna present you is my recent work, Beancraft. We will be talking about my dedication and what we have done, what we wanted to do, and the lessons learned along the way. Okay, the first question I want to ask before this presentation is, what are actually needed in reversing? I've been talking about this with my team members for many times. While you reverse, there's a lot of things you might be needing. Things like retyping variables, renaming variables, but first you need the basics, right? Which is F5 in IDA, the decompilation functionality. Time just passes. Many years ago, we still have the gut to reverse any instruction set by just looking at the raw disassemblies. But that time will never come back again. Now many people just can live without F5, without decompilation. So, let's get real. All analysis we need in actual reversing can be categorized in static analysis or dynamic analysis category. Listing every analysis in these two categories is not quite possible here, since there are so many of them. I listed what is the most important ones. Like in static analysis, a reverse tool must have disassembly to be called a reverse tool. If you are hardcore enough, decompilation is not a must. But people don't do that in this age now. We definitely need decompilation for real-world reversing. As for dynamic analysis, two things I can think of while reversing is debugging and emulation. Debugging allows us to inspect the internal status of the program during the runtime. Many of the time, when the binary to reverse is absurdly complex, debugging the internal is the only technique we left for understanding how it works. You set the breakpoint, run it, check those register values and memory values, and then continue again. Those values can reflect the logic behind the binary. Sometimes you can even guess the algorithm and verify that by inspecting only the internal status like the register values and memory values. As for emulation, emulation is mostly needed when I saw some binary has the runtime extraction technique used. With that, those binaries can prevent you from reading its internal logic without running the program. Or, if you have the time for that, you can just reverse it from the very beginning and completely understand the extraction logic, then do it statically. But that's just a rare case. And since the extraction logic may not be used elsewhere, if you do that, you waste a lot of time on that. Which for me, I think is not needed. So we just do emulation, get the result, patch it back on the binary, and check the decompilation. That is how things work in this age. Consider those functionalities. What do we have now? IDA is definitely the ruler without any question. I can say that its decompiler is the state-of-the-art level, since I know quite some research papers claiming that they have better decompiler compared to IDA, but it's undeniable that IDA has at least the world's first-class decompiler. They have tuned it for many years. One thing I learned in playing with decompiler technology is that making the decompiler work is not that hard. Many people overestimated the complexity of implementing a POC-level decompiler, but what makes it complex is that you need to adjust the decompiler to fit into many corner cases. You never know what people would use the decompiler for. Many algorithms used in the decompiler have to deal with those special cases. That's why you need a lot of time fixing those problems. And IDA, for sure, with these years of fixing, they made the decompiler quite reliable. At least no other project can go beyond them in the industrial area for now. Apart from IDA, we still have some choices, like Ghidra, NSA open sourced, which is our topic. I will talk about it later. Next, we have Binary Ninja. It is a nice project if you ask me. Although commercial, it has an intriguing design of the decompiler procedure. They made it into several phases, and each phase you get the result that you can read. In this way, they don't need to implement a decompiler immediately. During this phase, they gradually make disassembly, graph view, then each phase of the compilation output works, and the APIs are quite complete. But the problem is they don't have it open source and they still need more time to make it as complete as IDA. That decompiler still needs more fixings. It is a binary analysis framework, but as far as I know, they seem to be moving to complete reverse engineering tool recently. The decompiler seems to be commercial while the basic binary analysis thing is open sourced, and the decompiler is not out yet. The last one I want to talk about is Reader 2. I totally like their philosophy. The Unix-style reverse engineering tool really creative. But when doing the reversing, the command line interface compared to graphical user interface is not that convenient after all. During reversing, you may have multiple views simultaneously. One display the disassembly, one display the structures you identified, and even one more for decompilation. If you do that in the command line, you may waste too much time on inspecting those information. So for me, it is interesting but not too good to be used in real-world reversing. And one thing they lack is decompilation. I know about some efforts being made to Reader 2 to integrate Ghidra or other decompilers, but still it is an integration. You need to translate things around several intermediate representations to make things just work. Sometimes it does not work so well. They also provide a graphical user interface called Cutter, but the internal remains the same. You may say that I'm a bit biased, but in real, I just haven't used it for serious reversing tasks. Maybe, just maybe, it is because I got so used to IDA and can't move to a new type of working flow. Anyway, that's my comment. So, to be honest, the only one that I would like to use in real tasks is Ghidra. If I have to choose in those tools except IDA, especially if I wanted to choose between the open source ones. For me, open source is an important issue as sometimes when I got into a problem, I usually don't want to wait for the solution. That would take quite some time. And one more thing, I am always the curious baby wondering what is the cause of such software bug. Not knowing the reason behind the bug is killing me. That's why I always prefer open source softwares. Let's get back to the point. Ghidra is open source in 2019, written in Java and native language such as C++. It actually has not fixed the native languages you can use since the Java would interact with the native language in RPC protocol. This would be talked about in the detail when we get to the Ghidra decompiler internal part. What I care is that Ghidra has an almost complete feature set. That is, we have decompiler working, graph view working, debugger working. This is not a complete list. In short, most of the things you might expect in IDA is just there in Ghidra. And the extensibility is extremely good as they use Java for that. I know many people complain about how Java gets unreasonably long, but let's just admit, Java suits perfectly when you need such extensibility. The scripting interface provides you with Java language scripting and the Python scripting with Python. One thing I can think of that fails is Python can only support Python 2, and this might not improve in quite some time. And the plugin, import a jar file, and you are good to go. When developing the plugin, you have almost the full power of Ghidra. Call any method you like. It's just like developing part of the Ghidra itself. Even Ghidra itself uses the plugin system to make the code more organized. Also, Ghidra has a great architecture that I am referring to the Slay DSL. Slay is a programming language developed in the Ghidra project. It is a DSL describing the relationship between binary, the IR, and the assembly display. In this way, you don't need a meta language to write down logic describing how the binary lives to IR and how the binary should be displayed in assembly languages. You only need one such DSL for that. To make this clear, you write a Slay language code, you get a disassembler and a decompiler. That I think is one of the strongest features Ghidra has comparing to other tools. To sum up a little, Ghidra is the only one in the open source world that competes with IDA. Man, how I wish Ghidra is just that perfect, but the world doesn't go that way. Since Ghidra is a project of at least 20 years of developing, the historical issue is becoming its problem. We have historical code in Ghidra, and we might also encounter historical user experience issues. This is one example of the historical code issue. The C99 types are now a standard, but still Ghidra decompiler is not using them but use something their own. This kind of thing is quite common, especially in the decompiler code, especially about the coding style. Some of the coding styles are proved to be bad practice in these years, but those code cannot go away in the decompiler in a single glance. And because of those code, the developing of such components can be quite hard, which prevents people from introducing interesting features. As for the experience problem, you can clearly see that in the UI interface, right? The UI interface feels so much like I was in the last century. I know some people don't care about the UI interface when reversing generally, but this is just an example. For many people, this is where the first thought about Ghidra goes in. So I admit that Ghidra is a rather good project, no doubt. It is already nice enough to be used in many of the time. People around me always use Ghidra when their IDA is not working. Like before, when we encounter MIPS binary, we always use Ghidra. But is that it? We just let Ghidra that way and only take it as the replacement when IDA is not working? I want more than that. I want a project in the open source world that can grab some of the IDA users away instead of just staying as a replacement. I know that's a long way to go, but we need to work out the first step. The plan is simple. We just modernize everything got into our site. Modernize the experience, UI if you want an example, add modern features apart from the vanilla Ghidra ones, and hopefully we can also refactor the code to make that modernized as well. But that I know would take away quite some time. So we might do that gradually, step by step, and for each step, the project should stay working. We never thought about totally start up a new project and just give up the official Ghidra. That would take too much. And we also don't have that manpower for maintaining such a huge beast. So what are the differences? What I think is we improve Ghidra where we use it. In this way, we know what Ghidra lacks, and since we know the internal of Ghidra, we know how complex it is to implement the feature we want. We play CTFs, and that can be a quite good experience for tuning Ghidra. It's like extreme tests. My wish is that by using this way of improving, we can better understand of what we need as we are both the developer and the user. I know some of you might think, okay, so you have ideas about Ghidra, you can develop those features and you don't have enough manpower to develop your own. So why not just contribute that to the main repository? Well, that would need some explain. I'm not gonna deny that initially I wanted to do that this way, but later I found that people all have different tastes. This happens when adjusting decompiled coding style or user interface. There's no such thing as ground truth in decompiled code if you ask me. I think the decompiler is never about recover the original source code with only the binary, but to give you more insight of how the original source code works, and the decompiled code could make your life easier since you don't need to read raw assemblies for understand that. That is, we do not have a style that we all accept. Thus, we always have the choice to make it style A or style B. This is the same for UI as well. And for this project, when I decided to make it separate, I was thinking about making it a different choice. We have a different flavor, and if you don't like Ghidra's solution, you may choose ours. One more choice is always good for this world, isn't it? To ease the maintenance, we will be following the upstream closely, and if some of our features not about flavor issue, we will still send that to the upstream. So I'm not starting up a new religion like Minecraft versus Ghidra, no worry. Okay, the name of the project, as I mentioned, is called Minecraft. So what is Minecraft? I designed Minecraft as a collection of Ghidra related projects, or a Ghidra release. Now, Minecraft has several projects. First is our main topic today, GhidraCraft, which is a fork Ghidra following what rules we talked about already. The second one we have is Slaycraft. I already mentioned Slay DSL about what it is in general and how it provides the extensibility. I believe you already know how great it is, but unfortunately it is designed to be used in Ghidra internally. So Slaycraft is to save you from that. We provide APIs in different programming languages to use the Slay engine. With that, you can do what Capstone is capable of, and you even get the IR out of it. And PickledCraft, a Rust API to abstract away Ghidra's decompiler. We tend to use that to complete our refactoring job and to split the vanilla Ghidra decompiler into several reusable algorithms. It is still not completed yet, and so we will not talk about it in detail today. Minecraft is the name of the collections. The reason we organize it this way is we may have many more projects according to our plan, and many of them might be closely related. So this collection could give you index to those projects. Let's get back to the GhidraCraft, the main player we are gonna talk about today. Till now, the modernization is still in progress. We have already done several tasks which I would like to share. First, we have the decompilation improvements. This is more like a normal improvements, but during that, we face the flavor issue and tuning the style our way. Next thing to have is pickled patch feature. This is the very first feature apart from the improvements. You will get an idea of why we choose to do that shortly. And finally, we have partially modernized UI style. Let's dive into the first part, about the decompilation. You see, every time the IDA upgrade is out, it would have an item saying that it did minor decompiler improvements. Before doing this, I always think I can solve so many problems in the decompiler. It turns out I was being too young. The decompilation process is complex. The code, the algorithm, the architecture are all complex, especially when it is in C++ without modern C++ features. References and role pointers are everywhere, and Ghidra even did a using namespace std before every source code. I have to admit, this one is quite difficult to tune. I will talk about some of it to give you a basic idea of how difficult it can be. A little bit about Ghidra's decompiler first. The overall structure is clear, nothing special. If you know that, this is exactly how VS Code language server protocol would do. A custom RPC protocol is used to interchange data between the Java side and the C++ side. Actually, the Ghidra requires you to use such a way to connect Java world and native world. That's why when you need to write a plugin with native languages, you can always choose the one you like, as long as the RPC is working. Anyway, the RPC protocol used by the Ghidra decompiler is in XML format, mixed with binary values to mark starting and ending of a single packet. Each time Ghidra decompiles any function, it launches the process, send the previous result in XML format, and the C++ executable deserialize it and does the decompilation, send the decompiled result back in XML format. Just to mention that the XML format is treated in Ghidra code as if it were a string in many places. So if you'd like to add one more object that is both serializable and deserializable in Java and C++, you have to define the serialization and deserialization yourself. That is one place where your code gets very large. About the C++ world, it is more like a traditional compiler architecture, just like LLVM. We have the actions, which might be called passes in LLVM or some of the compilers. The global context is called architecture to provide architecture-specific information. Per function data is called just func data. Almost all the data in C++ world, like architecture or func data, is serializable and deserializable. That is a requirement for Java world to have full control over C++ decompiler. You see the problem here. There will be many code describing the serialization protocol, and we don't have a DSL to describe such thing to make life easier. Once the protocol requested some result, the actions are run. Each action performs one of the steps required by the decompilation, the actions work on the IR, manipulate them, extract information, record it into the funcdata or architecture. Finally, when we are all done, the pseudocode is generated by a language printing component in XML format. Then the result is fed into the protocol again to reach Java world. As you can see, the central of the decompiler is the IR they used, called pcode. The actions perform manipulation by inserting, removing, or modifying the pcode IR. The IR is designed to be suitable for low-level analysis. It was originated from an IR between the translation of two instruction sets. They model all variables as var node, identified by three parts: the address space, offset, and size. The address space is just like a piece of memory, or a huge array if you like to think it that way, along with the name. Some names have special semantic like register, RAM, which is used as memory. Temporary values are in unique space. Even the constants or immediates have a space, named const. But that is a special space, it is not a huge array. The offset in constant space is treated as the constant itself directly. One thing I feel quite intriguing in this kind of design is that how they model the registers as just a plain piece of memory. Normally, registers are modeled as it is. We have register names and size for each of them. But if you consider the overlapping between registers, that kind of model could just make things really complicated. As for pcode, we see that, for example, the zero offset in the register space under x86 is RAX. Since we have the overlapping, EAX register is easily modeled as the same offset but different size. Operations are just normal operations like you may encounter in any RISC-like instruction set. There are some special operations we need to care about, for example the multi-equal instruction. This instruction is not intended to be used after the lifting, but to be used during the decompilation. Multi-equal instruction is the fine node of SSA form. It is internal to the decompiler itself. By using such instructions, the internal form such as SSA is still in valid pcode, and we don't need a different data structure to store them. This is the overall structure of the decompiler, the actions that are run when a function is requested to be decompiled. It would be too much to talk about this in detail, since it is not the goal of this talk. I am just putting it there to have you understood how complex the decompilation process can be. So let's get back to our tasks. First thing to ask is, what things should be done to improve the decompiler? To balance between the implementation difficulty and its benefit during real-world reversing, we have selected out some of the goals as the first step. Those include the appearance of the magic functions such as concat or the ext, the lengthy default variable names, the analysis failure, and more minor problems. About the magic functions, this happens a lot in Ghidra. Sometimes, when we reverse binary, those functions like concat44 or zext8 just come out of nowhere. Since usually we don't have those functions in C language, without documentation, we will definitely have a hard time guessing what those mean. It turns out, they are just pcode that is not translatable. Concat or zext is the pcode instruction. For example, the concat44 is just concatenating 4 bytes and 4 bytes to form an 8 bytes variable. Comparing to IDA, I found that IDA tries its best to not show those magic functions, but this does not seem to be the same in Ghidra. And following IDA's idea, I think we have a better way of showing this. As a result, we added a rewrite rule to convert the concat instruction into typecasting and normal arithmetic operations. Just to mention, while the rewrite rule, we found Ghidra decompiler does not have an abstraction of rule matching and rewriting like in LLVM. LLVM has an AST matching DSL, which makes writing such matching convenient, but in Ghidra, you are on your own. In the future, when we decide to refactor this part of code, we might add that. About the default variables, current Ghidra's variable names are way too long compared to IDA. I totally understand the reason they do this, since they do not choose the way IDA did, use a shorter name and add a comment introducing extra information like the offset of this stack variable, They decided to add everything in the variable names, but the outcome seems to be too verbose when reversing a large function, and since we get used to IDA's way already, we decided to change that. This is not difficult, but just a user experience issue, and we made it into an option, so we give you the choice. Okay, the next thing we have is what matters the most, the analysis failure. Take a look at this picture. This is from a DEF CON Quotes challenge this year, called RAD. The challenge is written in Rust, and as you can see, the output code is totally not readable. There are plenty of assignments to an array that appears to be a magic number. If you take a look carefully, you will notice that this assignment all happened before a call to a function. And yeah, as you might guess, this number is where the function should return, i.e. the next instruction address after the function call. All other stack variables have this problem as well. The simple operations are translated into a store into stack space. There's a variable that contains a lot of f's in its name that is actually the stack base of this frame. So all other stack variables are not analyzed out. Instead, they are all translated into the relative addressing with reference to the stack f blah blah variable. Also, all the function params are just gone. After that CTF, I played with it a little bit and fixed these two problems: stack variable analysis failure and function params analysis failure. At the time of DEF CON, we used IDA to reverse this challenge. IDA also suffers from the function params failure, but is doing better in the stack variable analysis. Actually, that is one of the most important problems, as without the stack variables, the decompilation result is not useful in the end. Especially because of Ghidra's mechanism, you can never get rid of this assignment of the return address. Let's talk about the stack variable analysis problem first. To understand this problem, you will need to first understand how the stack variable analysis in Ghidra works. I'm not gonna lie, this takes me quite a while. It is not because Ghidra has no documentation about it, it is because the documentation is not something for me, I think. You may need to read the code again and again, and the documentation as well, to fully understand the mechanism. Anyway, about the stack variable analysis in Ghidra, the actual algorithm is way more complicated than this, but this should give you the idea. Ghidra first marks out the input RSP, the initial RSP value of this function that is used with but not defined. Let's give it another name, RSP0. Note that Ghidra does not do any interprocedure analysis, which means when it decompiles a function, it does not take any look at any other functions inside. After that, Ghidra will run a constant propagation procedure. This constant propagation procedure is not specific to this analysis, but its result is used here. Then, Ghidra thinks, after the constant propagation, all the RSP values should be marked now, in the form of input RSP or RSP0, adding a constant. If it is not in this form, for example, if you got RSP0 multiply something, then it is not possible to be treated as stack variables. And what causes the problem? Initially, at the very beginning of the Rust compile function, there's an RSP constant instruction. After the AND instruction, the RSP values are now not RSP0 and a constant. What we have is RSP0 and a constant, then add another constant. In this form, Ghidra thinks, okay, you're not a stack variable, then how about we treat you as an offset into the variable that equals RSP0 and C. About the magic numbers, these are return addresses. I already mentioned that. The reason behind it that Ghidra treats the return operation as if it were an indirect branch. So it does not do anything about store the return value. So the store return value operation is explicit. Once the stack variable analysis fails, it has no idea that this is a store of a return value. It sees it as a normal assignment. That's why we get our final decompiled output full of such return address assignment. As for the empty params problem, this one is not that annoying, but still I decided to fix it since I met it. That is my philosophy. At least I should fix things I met. This problem is caused by the dwarf debugging information handling. Usually, as in C or C++, where you do not specify -g to enable debugging information, the debugging information is not generated. But Rust does this in a different way. It always generates the debugging information, but if you do ask for optimization, it generates incomplete debugging information. Params information is one of the example. It generates function names but not params. Then Ghidra's devolve handler thinks we have a function but no params. That gives us this situation. IDA also suffers from this problem. Rust is just not that supported by the reverse engineering community for sure. So next time you want to protect some important code, just use Rust. The result is that we fixed this by adding this special case, and the pull request is already merged into the upstream. And we have minor bugs such as the wrong display of the string in the decompiled panel. As I remembered, IDA also suffers from this problem. Golang and Rust compiled binary has a different layout of string. Multiple strings are put together, and that confused the decompiler display. This is not a bug worth noting too much. The fix is still in the pull request list of the upstream Ghidra. Okay, enough of the fixes. Let's talk about the feature. A feature called pcode patch has been added to our Ghidra craft, which is responsible for modifying program semantic. What makes things different is that we support both manual patching and scripted patching. Many of you might already know that. IDA also has such a functionality, but all in all, we are still different. IDA calls this IR patching microcode API. You can insert a phase into the decompiler pipeline to manipulate the IR when decompiler is run. Our way of patching is not in the decompiler pipeline, but instead before the decompiler is run. This allows us to achieve manual patching. By right-clicking on the pcode, you can patch, insert, or remove the pcode before the decompiler runs. In this way, we get a more interactive analysis loop. We inspect, patch the pcode, then inspect again quickly. No need to write the script for that. The manual patching follows what is called raw pcode format. The pcode instruction contains var node and operations. Each var node contains 3 parts: the name, offset, and size. The operation names follow Ghidra official reference to pcode. Here we have an example of this syntax. In this sentence, we're adding 2 constants. First one has offset 8 and size 8. Second one has offset 16 and size 8. As I said before, the offset to the constant space is the actual value of the constant. Then the value gets assigned to the unique space variable offset 0x1234, which should be a temporary value. As for scripting, you need to have the instruction instance to patch pcode. This is because pcode is always attached to a single instruction. Then you can parse the raw pcode syntax with pcode raw parser to get a pcode array and patch it on the instruction to modify its semantic. When I initially wrote this, I have thought about 3 use cases. First one is to quickly modify program semantic that we have already discussed. You can do things like modify part of the decompiled program by its pcode, then inspect the result instantly. I know that if you patch the bytes on the instruction, you can also get similar result. But the difference is, sometimes there are only little space you can put in the instruction bytes. But if you patch the pcode, you don't need to care about that. Another thing to mention is the obfuscation. The same as above, you don't need to worry about length. That is the major reason we still provide a scripting interface. And the final one, I like this one the most, is to allow total custom decompilation. You provide Ghidra the pcode IR, it gives you the decompiled code. I really like this use case. We'll be talking about it later in detail. A simple example of the first use case. This is a real example of my reversing a CTF challenge. The challenge uses runtime extraction techniques to extract the basic blocks one by one. I used the emulation technique to deal with that, and successfully got all the basic block instructions out. The next problem I have is to connect those blocks together to get the full decompilation. This should be normal if you could just patch the jumping instruction at the end of each basic block. However, this is not the case. The challenge uses an ending mark to mark the end of each basic block, and a handler to handle such ending mark when it is there. Long story short, I was left just 2 bytes, but I need to patch a jumping instruction there. Then I used Pico patch to just patch the branching in Pico, and I got the decompilation working. Deobfuscation is nothing special. To demonstrate that, we wrote a simple script to deflatten the control flow flattening contained in the OLLVM obfuscation framework. This script is provided in the GidraCraft repository as well. Searching for LLVM in the script manager, you will find it. It works under multiple architectures. Now let's get to my favorite part, the custom decompilation. You patch the IR, get the decompilation. Let's think about it first. What is the normal way of decompile a custom instruction set? Because of the SLAE engine requirement, we at least need to specify how to parse the binary into a tree, how to display that tree, that is to display the disassembly, and then to translate the tree into a piece of Pico. This is not a problem if you are really dealing with an instruction set, but what if you are not? That is where we need the custom decompilation. Actually, this should be just a trick leveraging the Pico patch functionality. To do that, you can set up a new segment, add an op instruction there, then patch the Pico to that place. Once you've done that, you get the decompilation. In this way, what you are doing is bypassing this SLAE engine so that you don't need to provide the complete SLAE DSL, which sometimes is an overkill, or sometimes you just can't do that. Under some circumstances, you might be needing that, like a weird instruction set. You know how it can be translated into Pico, but the complete SLAE is hard to write. For example, if your instruction is in text format, no binary representation, then the SLAE engine is getting troubles. One example of that is the brainfuck language. It is an SOLAN. I've picked up its semantic here. You can say this language contains only several symbols, and it is quite low level. Each symbol is like a single instruction within an instruction set. We should be able to decompile this thing, but the problem is, if we'd like to do that, we have to go through the whole SLAE pipeline and write a SLAE DSL for that, which I think is an overkill. And brainfuck is kind of a special example that its symbol is all single characters. If you insist, you can still get SLAE working for brainfuck, but it is possible that we may have such an instruction set that has only text representation, that you cannot directly use the SLAE engine to handle it. This happens a lot in CTFs. So, what the result is like. These two pictures show you the result of decompiling a Hello World program in brainfuck. You can see that the looping is successfully translated, and by doing a little bit more to add a call to the write instruction, we made this even look better. I definitely would like to reverse this kind of code instead of original brainfuck code. I know you might argue that by translating the code into x86 or ARM, you can get this result probably as well. But the thing is, in that case, the temporary variables, like we used in unique address space, the one that I mentioned to store the temporary variables in P-code, you have to manage that your own. Not to mention that P-code is designed to be used between languages. It is no doubt more easy to use to translate into. As for the UI, we have also did quite some jobs to make UI feel better. Things including fix some classical stylings and add configurable color setting support. Ghidra has a lot of colors, and they are not equal. Some of them are configurable in the settings. A color picker is implemented for that. Some of them just follows the underlying Java Swing theme, but that's not all of them. Some of the colors are hard-coded into the Ghidra code. I don't know about the reason they do it initially, but that happens. It is not configurable, not in the settings or any kind of configure files, just hard-coded. The Java Swing theme is possible to be switched in Ghidra, and if you do that, those hard-coded colors appear to be really annoying. Some of them mess with the background and you can't see any characters. That's why we make that configurable with a color.properties file. But unfortunately, we can only do some of the adjust. The colors are too many in Ghidra and we can't just deal with it right now. We might use some helps on this. This is the demo of the UI for now. It is not possible to show you all the changes, but I think you get the basic idea. There's not much to talk about how we feel about the new UI interface. There are still a lot of things we can do. Fixing colors, dealing with Windows 98 styles, we have fixed some, but not all. This is not a really hard job to do, but we do need manpower on this. And what we have next is the Grill VM integration. This is a planned feature, but honestly, I just can't get it done in time before the presentation. But I think the idea is intriguing, so I decided to share it with you guys. What is Grill VM? It is one of the state-of-the-art technology in compiler area developed by Oracle. The idea is quite fun. By a reused Java hotspot JIT engine, Grill VM is able to JIT compile any programming languages, even low-level ones such as LLVM. What I like most is about the analysis part. Once you have the language implementation, it provides you with the general instrumentation framework, and the instrumentation should work under JIT. To us, this is definitely good news. We finally have the tools to achieve JITted binary emulation without too much of a work with the help of the Grill VM. Current implementation of the emulation in Ghidra is a nightmare. It is embarrassingly slow, and with the help of the instrumentation framework, we might even reuse the analysis designed for other languages. We need to have that consensus. Binary analysis is an extremely small area comparing to general programming language analysis. No doubt, those tools designed for other languages must have a better maintenance, and luckily, with this technology, we are finally possible to reuse them. We might have free tinted analysis or even symbolic execution for free. Well, if not, we might consider do that anyway. Grill VM provides a language implementation framework called Truffle. Truffle eases the usage of Grill VM by allowing us to write the interpreter, and we get the JIT out automatically by applying partial evaluation, one of the state-of-the-art dynamic compilation techniques. And this can be even easier as we don't need to design everything our own, as the Grill VM actually has an interpreter for evaluating LLVM bitcode, which is quite alike to us, called Ceylon. So, what we are gonna do is to add one more so-called language with the Truffle API as any other languages. This picture just depicts that. Since the P-code has so many things in common with LLVM, we are like just following their approach and get our things done. Allow me to pirate a slide from previous Grill VM's work for executing the LLVM. To execute LLVM bytecode, we need Ceylon to generate the LLVM IR, and Ceylon, what they developed to execute LLVM IR, receives the IR and uses the Truffle API to generate an AST. This AST is the base of the JIT compilation. Then this AST is sent to the JVM, where the actual JIT compilation or interpretation is happen. And for us, we are almost following the same approach. Use Truffle API to generate the AST for P-code. How they made Ceylon works for LLVM is out of scope. One can always refer to their publication to get what they need to know. I myself learned a lot reading those papers, and I read their code sometimes to understand how they get things done when I get into a problem. The developing procedure is split into 4 stages. By the time of this presentation, the first 2 stages are already finished. Because of current emulation code within Ghidra does not care about the extensibility, this code can be reused, is not abstracted out. We have to do the refactor first, that's why we have stage 0. Then, a POC interpreter implemented using Truffle framework is needed to prove our choice is possible, and to learn how the Grill VM should be used. Stage 2 and 3 is the next we are about to do. Do the true JITting following official Grill VM so long. And finally, we add the instrumentation tricks to the world. Initially, I thought about we could complete at least 3 stages before the presentation, but it needs more code than I expected. Most of the time I used to learn how Grill VM the another beast works. That's it. That's all the things we'd like to demonstrate about GhidraCraft. As for the lessons learned, Ghidra is really a huge beast that you can't handle in a short time. Sometimes the internal docs are missing, and you may cost quite some time to get why the code is written in this way, especially because it is huge and contains so many concepts. And the coding style is not quite modern. You may wonder sometimes why it is written in this way instead of some way you know better. It turns out those ways may not even exist when this code is written. But the advantage is undeniable. It is a complete thing. Many of the basic stuff you require to implement the feature or fixes are just provided. You can always refer to them to understand how things can be done. For that, I think we still need more time and a larger community to complete what we started. Thanks you guys again for listening this sharing. We really hope to have you with us. Since we follow upstream closely, it should be fine to experience the early development version. We are still working hard to provide at least a working build so you can at least feel it. And it's extremely best if you could join the development. Hope you guys enjoyed this presentation. See you next time.